video is for visually impaired students. Let's start physical properties and molecular structure from Pardeep's book. Introduction. The various methods used for the study of molecular structure may be broadly classified into two following types. Number 1. Methods based upon the study of physical properties of the substances such as number 1. Molar refraction, number 2 paracore, number 3 optical activity, number 4 dipole moment, number 5 magnetic susceptibility. 2. Spectroscopic methods such as rotational and vibrational spectroscopy, electronic spectroscopy, Raman spectroscopy, nuclear magnetic resonance spectroscopy. The study of molecular structure on the basis of physical properties is based upon the fact that the physical properties listed above are additive as well as constitutive. An additive property of a molecule is defined as that property, the total value of which is the sum of the values of its constituent atoms. A constitutive property of a molecule is defined as the property which depends upon the constitution of the molecules, that is, arrangement of atoms within the molecule and the presence of multiple bonds, rings, etc. in the molecule. Spectroscopic methods have already been discussed in chapter 3. Now in this chapter we shall take us a brief discussion of three important physical properties, namely optical activity, dipole moment and magnetic susceptibility one by one. Optical activity. Definitions. Plane polarized light. If a ray of light travels in any direction, it has vibrations in all directions at right angles to the path of propagation. If this light is passed through nickel prism, then the light which emerges out of the prism is found to have vibrations only in one frame. This light is called plane polarized light. The nickel prism thus used is called a polarizer. 2. Optical activity. If the plane polarized light is passed through a plate of quartz or turpentine oil or the solution of sugar, it is found that in the light that comes out, the plane of the polarized light gets rotated. Those substances like quartz, sugar, etc., which rotate the plane of the polarized light are called optically active substances, and the property of a substance to rotate the plane of the polarized light is called optical activity. The substances which rotate the plane of polarized light to the right are called dextrorotatory, and those which rotate the plane of polarized light to the left are called levorotatory. This method of observing the rotation of the plane of the polarized light is based upon the following principle. If the plane polarized light is passed through another nickel prism which has its axis parallel to the of first nickel prism, the light passes through the brightness is observed through the eyepiece. On the other hand, if the second nickel prism is placed with its axis at right angle to that of the first prism, the light is completely cut off and field of view in the eyepiece is dark. At all other positions, the brightness is less, but there may not be complete darkness. It is observed that if two nickel prisms are set at the crossed position so that the field of view is completely dark, and then the optically active substance is placed between the two prisms, the field of view becomes somewhat bright. The second prism has to be rotated through a certain angle about the line of propagation of light to get complete darkness again. This clearly shows that after passing through the optically active substance, the plane of polarized light has been rotated. The degree of rotation depends upon the rotation required to be given to the second nickel prism to get the darkness again. Thus, just as prism polarizes the light and is called polarizer, the second prism analyzes the light and is called analyzer. 3. Specific rotation. The angle through which the plane of polarized light is rotated on passing through the solution of an optically active substance depends upon the following factors. Number 1. Nature of optically active substance. Number 2. Concentration of the solution. Number 3. Length of the solution, that is length of the tube through which light passes. Number 4. Wavelength of light used. Number 5. Temperature of the solution. Thus, if m grams of the substance are dissolved in v ml of the solution so that the concentration of the solution is mYv gram per ml, L is the length of the tube in decimeters and alpha is the angle of rotation in degrees, then it is found that alpha is directly proportional to concentration in gram per ml into length of cube in decimeter. Alpha is equals to m by v into L. Alpha is equals to alpha gamma to t m into L by v, where alpha gamma to t is a constant character of the nature of the substance and depends upon the wavelength lambda of the light used and the temperature of the solution T degrees Celsius. If D line of the sodium vapor light is used and the temperature of the solution is 25 degrees Celsius, then it is written as alpha D 25. This constant is called specific rotation of the substance. Thus, from the above equation, alpha lambda to T is equals to V into alpha upon L into M. Now, if M is equals to 1 gram, V is equals to 1 ml and L is equals to 1 dm, then alpha gamma to T is equals to alpha. Hence, specific rotation of a substance may be defined as the angle of rotation produced when 1 gram of the substance dissolved in 1 ml of the solution, that is, concentration of the solution is 1 gram per ml, and the length of the solution through which light passes is 1 dm. In all reported values of alpha lambda to T, the concentration of the solution is taken in grams per 100 ml of the solution. Thus, if C grams are dissolved in 100 ml of the solution, then we may put M is equals to C and V is equals to 100. This equation gives alpha is equals to 100 into alpha upon L into C for solutions. Further, if instead of solution substance taken in a pure liquid or a solution, then M by V is replaced by density D of the pure substance, this gives alpha lambda to T is equals to alpha upon L into D for pure liquids or solids. In case of a pure solid, L is taken as the thickness of the solid in dm. Number 4. Molar rotation. The molar rotation is obtained by multiplying the specific rotation with the molecular weight m of the substance and dividing the result by 100 to reduce the magnitude of the number. It is usually represented as m lambda to T. Thus, m lambda to T is equals to m into alpha lambda to T upon 100. The instrument used for the measurement of the amount of rotation in degrees caused by an optically active substance to the plane of the polarized light is called a polarimeter. The principle of this instrument has already been discussed. It consists essentially of two nickel prisms, one called the polarizer and the other called analyzer. Both of these are fitted on opposite ends of the same metal tube. However, the polarizer is fixed, but the analyzer can be rotated about the axis of tube. In between the polarizer and the analyzer, there is a space for keeping the glass tube containing the solutions. The glass tube is usually 5 cm, 10 cm, 20 cm, 25 cm and has glass window on both ends. A circular scale is fixed on the metal tube near the analyzer. In the procedure, first of all, monochromatic light from a suitable source is passed through instrument without placing the tube containing the liquid or the solution. The light emerging out of the analyzer is viewed through eyepiece. The analyzer is then rotated slowly till the field of the view is completely dark. This gives the initial reading of the instrument. Now the tube containing the liquid or the solution is placed and the shutter closed. On seeing through the eyepiece, the field of view is no longer found to be dark. The analyzer is rotated slowly till the field of view is completely dark again. This gives the final reading. The difference between the final reading and the initial reading gives the angle of rotation alpha. If it comes out to be positive, the substance is dextro-rotatory, and if negative, it is levo-rotatory. Modern instruments have numerous improvements over the simple type. However, the basic principle remains the same. Optical activity and chemical constitution. Optical activity is a purely constitutive property, that is, it depends upon the arrangement of atoms within the molecule. It has been observed that the organic compounds which are found to be optically active contain at least one carbon atom to which 4 different atom or groups are attached. Such a carbon atom is called an asymmetric carbon atom and is usually shown by putting a sign of star over it. A very simple example of such a compound is that of lactic acid. It is found that such a compound exists in two forms, one of which rotates the plane of polarized light to the right is called dextro-rotatory, and the other which rotates the plane of polarized light to the left is called levo-rotatory. The two forms have the same constitution but differ in their configuration. Thus, the two forms are space isomers called optical isomers. Label 1 Hunt pointed out the difference in the two forms by suggesting that in case of such molecules, the asymmetric carbon atom is present in the center of a regular tetrahedron and the 4 atoms or groups attached to it are present at the corners of the tetrahedron. This gives rise to different spatial arrangements which were like the mirror image of each other. The above two configurations are different in the sense that they are not superimposable over each other. Thus, the two forms are related to each other as the right hand is to the left hand of the same person. The above two forms may be represented in a simplified way as follows. In form 1, the arrangement from H to OH is clockwise, and in form 2, the arrangement from H to OH is anti-clockwise. Hence, if one of them is dextrorotatory and the other is levorotatory, however, by mere inspection of configurations, it is not possible to predict as to which form is dextro or levo. The two forms are said to be enantiomorphs. Further, if equimolar quantities of the two forms are mixed together, a third form is obtained which is optically inactive. This is obviously due to the fact that the rotation cast by one form to the right is nullified by the equal rotation cast by the second form to the left. This process is called external compensation, and the substances obtained are called racemic mixture. This form can be separated into D and L forms by suitable methods. In case of compounds containing two asymmetric carbon atoms, a fourth form is also found to exist. In this form, the rotation cast by half of the molecule is compensated by the other half within the molecule as shown in the figure 5.54 tartaric acid. This form, which is optically inactive due to internal compensation, is called mesoform. Lastly, it may be mentioned that optical activity is found not only in the organic compounds containing an asymmetric carbon atom, but also in the compounds which contain other asymmetric atoms like nitrogen, sulfur, silicon, cobalt, tin, etc. Further, some compounds may not contain an asymmetric atom but are optically active because the molecule as a whole is asymmetric. Thus, it may be concluded that the optical activity is a property related with the asymmetry of the molecule. Hence, optical activity can be used to test the presence of asymmetry in the molecule. Dipole moment. General introduction. Polar and non-polar covalent bonds. A covalent bond is formed by the mutual sharing of electrons between two atoms. If the two atoms are identical, example in H2, Cl2, etc., the shared pair of electrons is attracted equally by both the atom, and hence it remains exactly in the center of the two atoms as shown below. Thus, neither of the two atoms in such molecules acquires positive or negative charge. The bond thus formed between two identical atoms is called non-polar covalent bond. On the other hand, if the two atoms are dissimilar, example in the HCl molecule, chlorine atom is more electronegative than the H atom, hence the electron pair is more attracted towards the chlorine atom than towards the hydrogen atom. In other words, the shared pair of electrons is more displaced towards the chlorine atom than towards hydrogen atom. As a result, the chlorine end of the molecule acquires a slight negative charge while the hydrogen end of the molecule acquires a slight positive charge. The bond thus formed between the two dissimilar atoms having slightly different electronegativities is called a polar covalent bond, and the molecule is called a dipole because it has developed positive and negative poles. Thus, the situation in HCl may be represented as shown in figure. Number 2. Dipole moment of a diatomic molecule. The extent of polarity of a molecule is expressed in terms of dipole moment, which is defined as follows. The dipole moment of a polar diatomic molecule is the product of the charge and each end of the molecule and the average distance between the centers of their nuclei, that is the bond length. In general, for a polar diatomic molecules A, B, in which one atom B is more electronegative than A, if plus q is the charge on the end A and minus q on the end B of the molecule, and D is the average distance between the center of their nuclei, then the dipole moment of the molecule AB is given by mu is equals to q into D. Obviously, if the molecule is non-polar, q is equals to 0 and hence mu is equals to 0. Number 3. Units of dipole moment. The charge present on the ends of the dipole of the molecule is usually of the order 10 ki power minus 10 ESU, and the distance between the atoms is usually of the order 10 ki power minus 8 cm. Therefore, mu must be the order of 10 ki power minus 10 into 10 ki power minus 8 is equals to 10 ki power minus 18 ESU cm. This value is called 1 dB. Thus, 1 dB is equals to 10 ki power minus 18 ESU cm. Vector nature of the dipole moment. The dipole moment is a vector quantity, that is, it has both magnitude as well as direction. It is therefore represented by an arrow pointing from the positive end to the negative end of the molecule. Number 5. Dipole moment of a polyatomic molecule. In a polyatomic molecule containing more than two atoms, every two bonded atoms have their dipole moment. This is called the bond moment. The net dipole moment of the polyatomic molecule is the resultant of the different bond moments. Obviously, the resultant will depend upon the direction of the bonds. Thus, if a molecule AB2 contains two AB bonds at an angle of theta and mu AB is the value of each bond moment, then the dipole moment of the molecule will be mu is equals to 2 mu AB cos theta by 2. As mu is known from experiments, therefore knowing the value of theta, the method is usually used for the calculation of bond moments. Alternatively, knowing the value of mu and mu AB in the method can be used for the calculation of theta and hence for predicting the shapes of molecules. The experimentally observed values of dipole moment of some common molecules and the calculated value of bond moments of some common bonds are given below. The resultant dipole moments of the groups like NO2, NH2, CH3, etc. have also been reported. These are called group moments. Their values depends upon whether the group is attached to an alkyl radical or an aryl radical. The value of a few groups are given below. A negative value of group moment means that the group is more electronegative, and a positive value means that the group is less electronegative than the alkyl or aryl radical. That is benzene ring. Electrical polarization of molecules. Every molecule is made up of positively charged nuclei and negatively charged electron cloud as shown in figure. The center of positive charge coincides with the center of negative charge. Hence, when such a molecule is introduced between the two plates of an electric field, the positive charged nuclei, hence the center of positive charge is attracted towards the negative plate, whereas the negative charge electron cloud is attracted towards the positive plate of the electric field. As a result, the molecule gets distorted as shown. This is called polarization of the molecule, and the distorted molecule with positive and negative ends is called an electric dipole. The molecule remains polarized so long as the electric field is applied but goes back to the original state as soon as the electric field is switched off. That is why this type of polarization is called induced polarization, and the electric dipole formed is called induced dipole. Since even after polarization the molecule is neutral as a whole, this means that the positive charge on one end must be equal to the negative charge on the other. Suppose this charge is q. If t is the distance of separation between the charges, then dipole moment of the induced dipole, called the induced dipole moment represented by mu t, will be given by mu I is equals to q into d. Evidently, the value of mu I will depend upon the nature of the molecule and the strength of the electric field. Say x, we write mu I is equals to alpha into x, where alpha is a constant and it is called polarizability of the given molecule. Alpha is further found to be related to the dielectric constant d of the medium present between the plates, that is the molecules being studied, according to the equation d minus 1 upon d plus 2 into m by rho is equals to 4 by 3 pi n into alpha. M is molecular mass of the molecule, rho is the density of molecule, n is Avogadro number. Clausius-Mosot equation. Suppose an electrostatic field is applied to two plates so that they are changed. Suppose the strength of the uniform electric field produced between them E0. Now, if a non-polar medium is placed between the plates, the strength of electric field will be reduced to E, because the induced dipole act in opposition to the applied field and hence partially neutralize the charge of the plates as shown. The ratio E0 by E is called the dielectric constant D of the medium. From electrostatics, it can be shown that E0 is equals to E plus 4 pi I, where I is the induced dipole moment per unit volume, that is I is equals to mu I into n, where mu I is induced dipole moment in a single molecule and n is the number of molecules per cc. Dividing both sides of equation 4 by E and putting E0 by E is equals to D, we get D is equals to 1 plus 4 pi I by E, or D minus 1 into E is equals to 4 pi I. The intensity of electric field strength X acting on each molecule is calculated by supposing that a unit charge is enclosed in a small spherical cavity which is large as compared with the size of the molecule but small in comparison with the distance between the plates. The electric intensity X is then made up of the following parts. Number 1. The field strength of the charge on the plates E0. Number 2. The charge induced on the surface of the dielectrics in contact with the plates is equals to minus 4 pi I. Number 3. The charge induced on the surface of the spherical cavity is equals to 4 by 3 pi r. X is equals to E0 plus 4 by 3 pi I minus 4 pi I. Substituting the value of E0 from equation 4, we get X is equals to E plus 4 pi I plus 4 by 3 pi I minus 4 pi I is equals to E plus 4 by 3 pi I. Substituting the value of 4 pi I from equation 5, it becomes X is equals to E plus D minus 1 by 3 into E is equals to D plus 2 by 3 is equals to E. From equation 7 and 8, A plus 4 by 3 pi I is equals to D plus 2 by 3 is equals to E. Or on putting I is equals to mu I into N is equals to alpha X into N is equals to alpha into D plus 2 by 3 into E into N. Equation 9 becomes T minus I by 3 E is equals to 4 by 3 pi alpha into D plus 2 by 3 E into N. Or D minus 1 upon D plus 2 is equals to 4 by 3 pi N alpha. If rho is the density of the substance placed between the charged plates and m is the molecular mass, then molar volume of the substance is m by rho. If n represents a Avogadro number, the number of molecules per unit volume is Np upon m. Substituting the values in equation 10, we get T minus 1 upon D plus 2 into m by rho is equals to 4 by 3 pi N alpha. As all quantities on the right hand side of equation are constant independent of temperature, therefore the quantity on the left hand side of equation must also be constant independent of temperature and depending only upon the nature of the molecule. This quantity is called molar polarization and is represented by P. Further, as the applied field produces an induced charge in the molecule by the relative displacement or distortion of the molecule, electrons and nuclei, P is often called induced or distortion polarization and is represented by Pi or Pd. Thus Pi or Pd is equals to D minus 1 upon D plus 2 into m by rho. Induced molar polarization is defined as the amount of polarization produced in 1 mole of the substance when placed between the plates of an electric field of unit strength. From equation 13, it is evident that the units of Pi will be same as those of m by rho, that is molar volume. Hence, Pi is usually expressed in centimeter cube per mole. Expression 13 giving the relationship between dielectric constant and polarizability was first derived by Mosotti and Clausius and is called Mosotti-Clausius equation. Effect of temperature on polarization. Using equation 13, the values of molar polarization have been determined for a number of substances. It is found that whereas molar polarization of number of substances such as O2, CO2, N2 and CH4 are constant and independent of temperature, the polarization values for some other substances such as HCl, CHCl3, C6H5NO2 and CH3Cl do not come out to be constant but decrease with increase of temperature. This observation has been the basis of measurement of dipole moment in the study of molecular structure as explained below. In case of molecules such as HCl, CHCl3, etc., their centers of positive and negative charges do not coincide with each other. Thus, they possess some dipole moments even in the absence of electric field. The dipole moment thus possessed by the molecule is called permanent dipole moment. In the absence of electric field, these permanent dipoles are oriented in a random manner due to thermal agitation as shown in figure. However, in the presence of an electric field, two disturbing effects takes place. These are: number 1, the electric field will tend to rotate and orient these dipoles in the direction of field. Number 2, the electric field will tend to polarize the molecule. If the molecules were stationary, the dipole would have been oriented perfectly parallel to the electric field, that is at right angles to the plates of the electric field. However, due to thermal agitation, they taken positive in between that of original state and the perfectly parallel state as shown at B in figure 5.1241 permanent dipole. Thus, in case of molecules possessing permanent dipoles, the right hand side of equation 13 will give the total polarization Pt, which will be the sum of induced molar polarization and the orientation molar polarization P naught. That is, Pt is equals to d minus 1 upon d plus 2 into m by rho is equals to Pi plus P naught. As mentioned earlier, the induced polarization was given by Closius-Mosotty equation. Pi is equals to 4 by 3 pi n alpha. The orientation molar polarization is given by the equation put forward by d by P naught is equals to 4 by 3 pi n into mu square upon 3 kt, where mu is the permanent dipole moment of the molecule, K is Boltzmann constant, and T is the temperature. Substituting the values of Pi and P naught from equation 15 and 16 in equation 14, we get Pt is equals to d minus 1 upon d plus 2 into m by rho is equals to 4 by 3 pi n alpha plus 4 by 3 pi n into mu square upon 3 kt. Measurements of dipole moment. First method is vapor temperature method. The above equation can be written in the form Pt is equals to A plus B upon T, where A is equals to 4 by 3 pi n alpha and B is equals to 4 pi n mu square upon 9K are constant for the given substance. This equation is primarily applicable to gases and vapors. Thus, if Pt is plotted against 1 by T, a straight line graph will be obtained. If the molecules possess permanent dipoles, the slope of the plot will be given by B is equals to 4 pi and mu square upon 9K. From this equation, the permanently dipole moment mu of the molecule can be calculated as all other quantities are constant whose values are known. Solving equation by putting the values of the various constant, we get mu is equals to 0.0218 under root b into 10 k power minus 18. The straight line plots for a few substances with and without permanent dipoles are shown in figure. It may be seen that whereas Pt varies with temperature for HCl and CH3Cl etc. possessing permanent dipoles, there is no effect of temperature on substances like CH4, CCl4 etc. which do not have permanent dipoles and hence possesses only induced molar polarization. Methods of measurement of dipole moment. As explained above, the basic equation for the determination of dipole moment is Pt is equals to d minus 1 upon d plus 2 into m by rho is equals to A plus B by T. A and B are constants. Thus, the experiment involves the determination of the electric dipole dielectric constant d and the density rho at the different temperature T. The value of Pt are then calculated and plotted against 1 by T. If Pt is found to vary linearly with 1 by T, the substance possesses a permanently dipole moment and the value of dipole moment mu is calculated from the slope of the line. On the other hand, if Pt is found to be independent of temperature, the substance does not possess any permanent dipole moment. The dielectric constant required in the above equation is determined by first measuring the capacity of a condenser in a vacuum between the plates and then measuring the capacity of the same condenser when filled with the given substance. The dielectric constant of the given substance is then given by d is equals to C upon C naught. Number 2. Refraction method. According to Closius-Mosotty equation, the induced or distortion molar polarization of the molecule is given by Pi or Pd is equals to d minus 1 upon d plus 2 into m by rho is equals to 4 by 3 pi n alpha. As d is a pure number, molar polarization P is simply molar volume of the material. Further, it has already been explained that it is independent of temperature if the substance is non-polar and does not have a permanent dipole moment. For such molecules, it was derived by J.C. Maxwell that the constant of a substance is related to its refractive index for the light of long wavelength according to the equation d is equals to n square. Substituting this value in equation 22 above, we get PD is equals to n square minus 1 upon n square plus 2 into m by rho is equals to 4 by 3 pi Na. However, n square cannot be found by extrapolation to infinite wavelength the values of refractive indices measured with visible light. This is because visible light can displace only electrons, whereas the positively charged nuclei remains unaffected. Thus, the distortion polarization can be considered to be the sum of electron polarization and atom polarization, that is PD is equals to PE plus PA. To find total volume of PD, it is therefore necessary to measure the refractive index using infrared rays because they can displace in heavy atomic nuclei as well as electrons, but measurement of refractive index with infrared radiations is difficult. Hence, the problem is solved by finding electron polarization by measuring the refractive index using visible light, that is P is equals to n square minus 1 upon n square plus 2 m by rho. As an approximation, 5% of this value is added to it. Account for Pa to get the total value of PD. Then, as before, total polarization of a molecule possessing a permanent dipole moment is the sum of two terms. The first called distortion polarization, the second called orientation polarization, due to permanent moment possessed by the molecules. Hence, we can write Pt is equals to Pd plus P naught. Putting the value of P naught from the by equation, P naught is equals to 4 by 3 pi n into mu square upon 3 kt. Equation 5 becomes Pt is equals to Pd plus 4 by 3 pi n mu square upon 3 kt. Putting the values of the constant and simplifying, we get mu is equals to 0.0128 under the root Pt minus Pd into T. Pt can be determined by finding the dielectric constant of the vapors at temperature T, and Pd can be found either by measuring the refractive index using infrared radiation or by approximation method explained above. This method is simpler than the temperature method because it involves the measurement only at one temperature. Number 3. Dilute solution method. Equation 20 is applicable to gases and vapors only. For substances which are not gaseous or which cannot be converted into vapors, the following procedure is followed. 1. A dilute solution of the given substance is prepared in a non-polar solvent such as benzene, CCl4, CS2, etc. The density and dielectric constant of the solution are determined at various temperatures. Number 2. At each temperature, the molar polarization of the solution PS is calculated using the relation PS is equals to D minus 1 upon D plus 2 X1 M1 plus X2 M2 upon rho, where X1 and X2 are the mole fractions of the solvent and the solution in the solution. M1 and M2 are their respective molecular masses and rho is the density of the solution. The molar polarization of the solution is related to the molar polarization of the solvent and that of solute. PS is equals to X1 P1 plus X2 P2. Thus, knowing the values of X1, X2 and P1, P2, that is molar polarization of the solute, can be calculated. Number 4. The values of P2 obtained at different temperature are plotted against 1 by T. The value of mu is then calculated from the slope of the line as explained earlier. Dipole moment and chemical constitution. Application of dipole moment. The knowledge of the dipole moment of a molecule can be applied in a number of ways to study its chemical constitution. Number 1. In comparing the relative polarities of molecule. For example, the dipole moments of HF, HCl, HBr, HI are 2.0, 1.03, 0.78 and 0.38 respectively. This shows that the polar character of the molecule decreases as we move from HF to HI. Number 2. In calculating the percentage ionic character of a polar covalent bond. For example, the dipole moment of HCl is 1.03 D. If the bond were 100% ionic, each end would acquire full 1 unit charge, that is 4.8 into 10 to the power minus 10 ESU. The bond distance in HCl is taken to be 1.275 Armstrong, that is 1.275 into 10 to the power minus 8 centimeter. Hence, if HCl were 100% ionic, the dipole moment would have been 6.11 D. Actual value of dipole moment of HCl is 1.03 D. Percentage ionic character of HCl bond is equals to 1.03 upon 6.11 into 100, that is 17% approx. Number 3. In predicting the geometry or shape of molecule, the fact that dipole moment is a vector quantity and that a particular bond has almost a constant value of bond moment is very useful in predicting the shapes of molecules. A few cases are described below. A diatomic molecule. A diatomic molecule is always linear irrespective of its dipole moment. Number B. Triatomic molecule. In triatomic molecule of the type AB2, there are two possibilities. Number 1. The dipole moment of the molecule may be 0. This shows that in these molecules, one bond moment is equal and opposite to the other, hence the molecule must be linear. Number 2. The molecule may have a definite value of dipole moment. Obviously, in these cases, the possibility of linear shapes is ruled out. The two bonds must have a definite angle between them, which can be calculated. If we know the bond moments, for example, the bond moment for HO is 1.60, the bond angle is calculated to be nearly 105 degree. Thus, H2O may be represented as shown in figure. Such molecules are called bent molecules and the shape is called V shape. C. Tetraatomic molecule. In tetraatomic molecules of the type AB3, the two simple possibilities are: Number 1. The dipole moment of the molecule may be 0. In such a case, all the 4 atoms must be in one plate and the angles between the bonds must be equal. Example, in BF3, such a shape is called planar trigonal. Number 2. The molecule may have some definite value of dipole. This indicates that one atom lies out of plane of the rest of atoms. For example, molecules of NH3 may be represented. D. Pentaatomic molecules. The pentatomic molecules of type AB4, which we commonly come across, are CH4, CCl4, SiCl4 and SnCl4, etc. The dipole moments of all these molecules is found to be 0. This is possibly only if these molecules have symmetrical or regular geometry to that of the different bond moments cancel out each other. The experimental facts confirms that these molecules have tetrahedral shapes as represented below. In differentiating the cis and trans isomer, the cis and trans isomer are represented as given below. It is clear that all the trans form will be non-polar, whereas cis forms will be polar. For example, in case of dichloroethane, cis form has been found to have a dipole moment of 1.9 d, while the trans form is found to have 0 dipole moment. 5. In differentiating the ortho-para-meta isomers, as benzene is a regular hexagon and its dipole moment is 0, therefore substituting two atoms or groups in the ortho-meta or para positions, the di-substitution derivatives will have different dipole moment isomers as shown below. 6. In spotting the possibility of resonating structures, for example, the nitrous oxide molecule has a small value of dipole moment if the molecule is supposed to have any one of the following two isomers. The dipole moment should be high. This confirms that N2O molecule is a resonance hybrid of the structure 1 and 2. Magnetic susceptibility. General introduction to some terms used. Number 1. Magnetic permeability. If two magnetic poles of strength M1 and M2 are separated by a distance of r, then the force affecting between them is given by F is equals to 1 by mu M1 into M2 upon r square. The quantity mu used in the above expression is called the magnetic permeability of the medium between the poles. It is defined as the relative tendency of the magnetic lines of force to pass through the medium as compared to that in the vacuum. For vacuum, mu is taken as equals to 1. Similarly, for air, mu is taken as approximately equal to 1. Number 2. Diamagnetic, paramagnetic and ferromagnetic substances. As mentioned above, for vacuum, mu is equals to 1. For other media, mu can be less than or greater than 1. If mu is less than 1, then the magnetic lines of force prefer to pass through the vacuum rather than through the substance comprising the medium. In other words, the magnetic lines of force are repelled away from the substance. Such substances are said to be diamagnetic. On the other hand, if mu is greater than 1, then the magnetic lines of force have greater tendency to pass through the substance rather than through the vacuum. In other words, the magnetic lines of force are attracted towards the substance. Such substances are called paramagnetic. If mu is very high, the tendency of the substance to attract the magnetic lines of force is very high, and the substance is said to be ferromagnetic. Ferromagnetism is exhibited mainly by iron, cobalt, nickel, and their alloy. It is a property of greater interest in the subject of physics. Only in chemistry we deal only the diamagnetism and paramagnetism. The behavior of diamagnetic and paramagnetic substance in a magnetic field is shown. Number 3. Magnetic susceptibility. As seen above, if any material is placed in a magnetic field, the strength of magnetic field in the material is different from that air in the vacuum. The strength of magnetic field thus present in the material is called magnetic induction. If H is the strength of the applied magnetic field and B is the magnetic induction in the given material, the two are related according to the equation B is equals to H4 pi I, where I represents the magnetic moment per unit volume in the material and is called intensity of magnetization. It may be positive, negative depending upon whether the material is paramagnetic or diamagnetic. The intensity of magnetization produced per unit strength of the applied magnetic field is called specific magnetic susceptibility. It is usually represented by X. Thus, mathematically it is equals to I by H. It is the quantity which is usually measured experimentally in the study of magnetic properties of different materials. Multiplying the specific magnetic susceptibility with the molar volume of material, we get what is called as magnetic susceptibility per mole or molar magnetic susceptibility. It is usually represented by xm. Mathematically it is equals to m by rho into 1 by h. The molar magnetic susceptibility may be defined as the intensity of magnetization induced per mole of the material by the unit field strength. Quite often it is convenient to deal with the quantity xm in place of x. Further, the magnetic induction B is related to the strength of applied magnetic field H according to the equation B is equals to mu H, where mu is the magnetic permeability of the medium, that is I is equals to xh. Substituting the values of P and I from equations, we get mu H is equals to H plus 4 pi xh. Mu is equals to 1 plus 4 pi x. Since I in the above discussion is the magnetic moment per unit volume of the material x, in fact the volume susceptibility of the medium. However, for most of the practical purpose we use mass susceptibility. It is obtained by dividing the volume susceptibility by the density rho of the material. Hence we have mass susceptibility is equals to susceptibility by rho. So substituting the value in equation 7, we get mass susceptibility is equals to mu minus 1 upon 4 pi rho. This gives the relationship between the specific magnetic susceptibility and the magnetic permeability of the material. Since for diamagnetic substance mu less than 1, therefore the specific magnetic susceptibility is negative for such substance. On the other hand, for paramagnetic substance mu is greater than 1, therefore x or x dash is positive but small. For ferromagnetic substances, as mu is very large, so this is also very large. Measurement of magnetic susceptibility. Gauss method. The magnetic susceptibility are generally determined by the method put forward by Gauss in 1889. It is shown in figure 5.20 and is briefly explained below. The material under examination is taken in a thin cylinder or a tube, which is then suspended vertically with a wire from one arm of the balance between the two poles of the electromagnet, such that the lower end of the cylinder is nearly in the middle of the poles of the electromagnet. The cylinder is now counterbalanced in this position by placing weights in the other pan of the balance. The current is now switched on into the electromagnet. If the substance is paramagnetic, the cylinder will be pulled down so that more magnetic lines of force can pass through it. On the other hand, if the substance is diamagnetic, the cylinder will be pushed upward. In the first case, some extra weights will have to be added into the pen, whereas in the second case some weights will have to be removed from the pen to restore the balance. Since the change in weight is equal to the magnetic force acting on the material, hence if delta m is the change in mass, then we have delta mg is equals to 1 by 2 psi minus psi a h square, where g is the acceleration due to gravity. The delta mg gives the change in weight. The right hand side is a magnetic force acting on material of volume susceptibility, when A is the area of cross section, h is field strength, and psi a is the volume susceptibility of the air. In the above calculations, the absolute value of the field strength H is also required. However, the necessity of measuring H and A can be eliminated if the experiment is first performed with substance of known susceptibility using the same magnetic field and the same cylinder. For taking this substance, usually water is taken as a standard substance for this purpose. This evidently we will have delta ms is equals to psi s minus psi a upon delta mw is equals to delta s psi w minus psi a. Magnetic susceptibility and molecular structure. A detailed study of the magnetic susceptibility of a large number of organic and inorganic compounds has revealed that, like many other physical properties such as molar refraction, paracore, etc., the molar magnetic susceptibility is an additive as well as a constitutive property. The values assigned to the various atoms to the structural factors can be obtained from the experimentally determined values for a large number of elements and compounds. The values of magnetic susceptibility for some of the atoms and structural groups are given in table 5.3. Explanation for diamagnetism and paramagnetism. Electrons in an atom have orbital motion as well as spin motion. As they are charged particles, therefore their motions produces a small magnetic field. If all the electrons in a molecule are paired, the magnetic moment of the electron spinning in one direction is cancelled by the magnetic moment of the electron spinning in opposite direction. The net result is that the substance has zero magnetic field. If such a substance is placed in a magnetic field, small magnetic moment is placed in the substance in opposition to the external magnetic field. As a result, the substance is repelled by the magnetic field. This type of behavior is observed for diamagnetic substances. Thus, diamagnetism is exhibited by those substances which contain paired electrons only, that is, no unpaired electron is present. On the other hand, if a substance contains some unpaired electrons, the magnetic moments of the electrons do not cancel out completely. Hence, the substance has a permanent magnetic moment of its own. In fact, each unpaired electron behaves like a micromagnet with a definite magnetic moment. If such a substance is placed in an external magnetic field, the micromagnets will arrange themselves parallel to the external field, and the induced magnetic moment is insufficient to overcome the permanent magnetic moment of the substances. Substances are therefore attracted by the magnetic field instead of being repelled by it. This type of behavior is observed for the paramagnetic substances. Thus, paramagnetism is exhibited by those substances which contain some unpaired electrons. Determination of magnetic moment of a paramagnetic substance. As explained above, each atom, ion or molecule of a paramagnetic substance behaves like a micromagnet with a definite inherent magnetic moment of magnitude μm. When such a substance is placed in the external magnetic field, the micromagnets tend to arrange themselves parallel to the applied field. However, this tendency is opposed by the thermal motion of the particles. Hence, the actual arrangement taken up will depend upon the temperature. Langevin in 1905 put forward the following relationship. Magnetic susceptibility is equals to alpha m into mu square m n upon 3 kt. N is a Avogadro number, K is Boltzmann constant, alpha m is a constant for given substance. Relationship between magnetic moment and the number of unpaired electrons. The total magnetic moment of any atom, ion or molecule is the sum of the following two values. Number 1, magnetic moment due to the orbital motion of the electrons. It is equals to L into L plus 1 under the root Bohr magneton, where L is azimuthal quantum number for that electron. Number 2, magnetic moment due to spin motion of the electron is equals to 2 into s into s plus 1 under the root Bohr magneton, whereas a spin quantum number having value equal to 1 by 2. If ions or molecules are considered instead of free ions, it is expected that the orbital motions of the electrons are tied into the nuclear configuration of the molecules or the ions so tightly that they are unable to line up with the applied magnetic field. Hence, the magnetic moment contribution due to the orbital motion is negligible. Thus, the magnetic moment of the molecule or the ion is mainly due to the spin motion of the electrons. Thus, we have mu m is equals to 2 into s plus 1 under the root Bohr magneton, whereas is represented spin quantum number of 4, 1 unpaired electron for a molecule or ion containing a number of unpaired electrons. The expression is usually written as mu m is equals to 2 into s plus 1 under the root Bohr magneton. For 1 unpaired electron, s is 1 by 2. For 2 unpaired electron, s is 1. For 3 unpaired electron, s is 3 by 2. And for n unpaired electrons, s is 1 n by 2. Mu m is equals to 2 into n by 2 plus 1 under the root. Mu m is equals to n into n plus 2 under the root Bohr magneton. Thus, knowing the number of unpaired electrons present, the magnetic moment can be calculated or vice versa. The expected values for the magnetic moment mu m for paramagnetic substance for different values of unpaired electrons are given in table 5.4. Relationship between molar magnetic susceptibility and the number of unpaired electrons. Taking alpha m to be negligible in equation 11 as it represents the diamagnetic molar susceptibility of the substance induced by the applied magnetic field, equation 11 becomes magnetic susceptibility is equals to mu square m into n upon 3 kt. Substituting the value of mu m from equation 14 in equation 15, we get magnetic susceptibility is equals to 7 upon 3 kt into n plus 2. The expected values of magnetic susceptibility for different values of n are listed in table 5.4. Applications of magnetic susceptibility. Number 1. In confirming the structure of given molecule. The use of molar magnetic susceptibilities in confirming the structure of a given molecule is based upon the fact that the magnetic susceptibility is additive as well as constitutive property, as already discussed. Number 2. In calculation of the number of unpaired electrons in a molecule or ion, knowing the molar susceptibility, the number of unpaired electrons present in a molecule or ion can be calculated using equation 16. This has helped in understanding the electronic structures of a number of molecules. For example, the molar magnetic susceptibility of oxygen has been found to be 3400 into 10 to the power minus 6, which shows that it must contain 2 unpaired electrons. Number 3. In the study of coordination compounds. The main application of magnetic susceptibility in chemistry has been in the study of coordination compounds of transition elements. Measurement of magnetic susceptibility helps us to know the number of unpaired electrons present in the complex, which in turn helps to assign the correct structure to the complex sign in some cases. For example, the magnetic susceptibility values of complexes Fe6 negative and Fe6 negative suggest that there is one unpaired electron present in the former, whereas there are 5 unpaired electrons present in the latter. These are explained by suggesting the following electronic structures. Number 4. In establishing the formula of certain compounds. For example, it has been shown that the formula of hypophosphoric acid is H4P2O6, not H2PO3. This is because if the latter formula were correct, sodium and silver salts NaHPO3 and Ag2PO3 would contain an odd number of electrons and should be paramagnetic, while actually they are diamagnetic. Hence, their salts must have the formulas NaH2P2O6 and Ag4P2O6 respectively. Similarly, the formula of the mercurous chloride is H2Cl2 and not HgCl. Number 5. In explaining the existence of odd electrons molecules. The compound containing odd electrons are expected to be paramagnetic. This is actually found to be so for a few gaseous compounds, the namely nitric oxide, nitrogen dioxide and chlorine dioxide. Moreover, their magnetic susceptibility show that they contain one unpaired electron in each case. Number 6. In explaining the formation of free radicals, some highly substituted aromatic compounds have a tendency to dissociate into fragments called free radicals. The existence of free radicals is supported by the fact that such compounds exhibit appreciable paramagnetism, which is explained on the basis that the free radicals contain odd electrons. The measurement of magnetic susceptibility of such substances even helps in the calculation of percentage dissociation of the substance into free radicals. For example, the paramagnetic susceptibility of alpha-naphthyl diphenhyl methyl is found to be 114 to 10 की power minus 6. The theoretical value for a single unpaired electron as shown in table 5.4 is 1216 to 10 की power minus 6. Hence, percentage of the compound dissociated into free radicals is 11%. Dielectric properties of solids. Insulators do not conduct electricity because the electrons present in them are held tightly to the individual atoms or ions and are not free to move. However, when electric field is applied, polarization takes place because nuclei are attracted to one side and the electron cloud to the other side. Thus, dipoles are formed. In addition to these dipoles, there may be permanent dipoles in the crystal. These dipoles may align themselves in an ordered manner so that such crystals have a net dipole moment. Such polar crystals show the following interesting electrical properties. Number 1. Piezoelectricity and pressure electricity. When mechanical stress is applied on such crystals so as to deform them, electricity is produced due to displacement of ions. The electricity thus produced is called piezoelectricity and the crystals are called piezoelectric crystals. Conversely, if electric field is applied to such crystals, atomic displacement takes place resulting into mechanical strain. Thus, such crystals act as mechanical crystal transducer. A few examples of piezoelectric crystals include titanates of barium and lead zirconate, ammonium dihydrogen, and quartz. These crystals are used as pickups in record players where they produce electric signals by application of pressure. They are also used in microphones, ultrasonic generators, and sonar detectors. Number 3. Pyroelectricity. Some piezoelectric crystals, when heated, produce a small electric current. The electricity thus produced is called pyroelectricity. Number 4. Ferroelectricity. In some of the piezoelectric crystals, the dipoles are permanently polarized even in the absence of the electric field. However, on applying electric field, the direction of polarization changes. The phenomena is called ferroelectricity due to analogy with ferromagnetism. Some examples of ferroelectric solids are barium titanate, sodium potassium tartrate, and potassium dihydrogen phosphate. It may be pointed out here that all ferroelectric solids are piezoelectric, but the reverse is not true. Number 4. Antiferroelectricity. In some crystals, the dipole align themselves in such a way that alternatively they point up and down so that the crystal does not possess any net dipole moment. Such crystals are said to be antiferroelectric. A typical example of such crystals is lead zirconate. Uses of above properties of solids. The various properties of the solids as explained above are being used in electronic and magnetic devices such as transistors, computers, telephone, etc. Thanks for watching.